Cheers. Thank you. My name is Ross Gibb. I'm here with my colleague, Josh Reynolds, and we're going to give you a talk about malicious Office documents and some threat intel projects we've been working on about them. So Josh and I work on the research and efficacy team at Cisco in the Calgary engineering office. So our job is basically to ensure the efficacy of the advanced malware protection suite of products that Cisco sells. So our job basically boils down to ensuring that we detect everything we should and nothing we shouldn't. So maximizing true positives and minimizing false positives. We both spoke at BSides last year in separate talks. We're really proud to be back this year to support a really well-organized and good conference. And we're both actually co-authors of the malware analysis course that's going to be offered in the second year of the brand new SATE IT security program, which we're also really proud of. Just a little bit about myself. I'm from Calgary. Previous to Cisco, I worked at IBM and Symantec in Calgary and in California. At Symantec, I worked on investigating targeted attacks and taking down botnets. When I'm not doing computer stuff, I like board games and politics, and Josh is just going to introduce himself.
So as Ross said, my name is Josh Reynolds. I also work on the same team as Ross, doing essentially the same things. My background is kind of varied. When I initially was doing my program at SATE, after my first year, I luckily got hired on doing QA for a local web consulting company. After I graduated from SATE, I went over to Australia to finish a bachelor degree in information technology. There I interned with Red Hat on their penetration testing team, and I wrote some web application fuzzing frameworks for them. Then when I came back, I did some system administration for Graycon while also doing a few penetration testing exercises for some of their clients. And then I came over to SourceFire in a QA role, and then once I began to show expressed interest in malware research, because that's kind of our bread and butter, I moved over to the team I am on now. I'll pass it off to Ross to move through some of our documents.
Cool. So the presentation is kind of in two parts. I'm going to cover the first part, which is going to be a discussion about trying to generate some threat intelligence information on like an aggregation of malicious Office documents. And the second half, Josh is going to be cover, and it's going to be a deep dive into a specific threat and threat actor. Okay, so what are the kind of clones that the title of the talk is referring to? And it's malicious documents that look kind of like this. If you have any kind of responsibility for email security at your company or your organization, or you have an email address, you may have seen documents like this. So what these are two examples of malicious Office documents with macros inside, and a macro is a tiny little program. And if you are enticed into enabling the content, that program will execute and most likely infect you. So what we typically see with these is an image is used. So this is actually, this blue background and white text is actually an image. And in this case, it's telling you that the current document was from an old version of Word and trying to get you to click the enable content. The second one here is very similar. They're actually showing obfuscated text here to kind of say, oh, it's scrambled and we need to update it. Here's a couple more. The one on the left has been really prominent over the last couple months. This looks like text, but it's actually an image. This is an image. Again, it's just trying to entice you. Everything is trying to entice you to click this button and enable the content. The one on the right is actually not using any images. So there's some obfuscated text, and there's like a line of English here to try to get you to enable it. Last one. The one on the left here is kind of well done. It sort of looks like an encrypted message, and there's an RSA logo to further that point. Again, everything's to entice you to click the content, and this is your 3-step plan to get infected. So again, okay. So how did we actually get here? So this part, I'm just going to cover a little bit of background if you don't spend a lot of time worrying about Office documents with macros inside them. So Microsoft Word was joined with Visual Basic. If You can kind of see how this might be a good idea. You can add a lot of rich content to Office documents with like having a real programming language embedded. There's some amazing spreadsheets that we've had detections on that were actually totally clean, and there's a lot of commerce conducted in this manner. But the problem from a security standpoint is when these two things combined like kind of lead you on a path to the dark side. Okay, so VBA kind of came into Word officially with Word 97, although previous to that there was something called Word Basic. As soon as VBA, which stands for Visual Basic for Applications, was integrated into Microsoft Word, malicious macros followed really shortly after. So attackers realized you could write a little program, email it to someone. As soon as they open the document, the program would execute, and you'd subsequently become infected. The famous one, if you ever read about the history of malware, is the Melissa virus. Macros existed, or malicious macros existed previous to Melissa, but the reason Melissa is famous is because it propagated itself. It would read 50 email addresses from your Outlook contacts and send itself to those contacts. As well, it was called a virus because it would infect your template on your local Office installation, and then every subsequent document you would create would have a copy of the Melissa virus. And it wasn't particularly malicious other than it swamped computer networks at the time, which weren't as robust as they are today, and brought down a number of computer networks at the time. So in 2007, Microsoft made some big security improvements in a lot of their products, or it was kind of leading up to this point. So in Office, they disabled macros by default, and we achieved peace in the galaxy. There was a lot, myself included, thought the problem was going to be solved once people had to click through something to enable macros. But like the Death Star that we have to keep destroying every couple of movies, bad things have a habit of coming back. So between 2007 and now, they didn't go away. There's a famous kind of hacking incident against the German Chancellor, Angela Merkel, in 2007 that was based on an Office document with a malicious macro. And there was a nice paper about how they were going to be the future of cyber war, the future munitions of a cyber war. And most recently, and I would, in my kind of like anecdotal, just being in the industry, around 2012, 2013 is when we started to see a lot of malicious macros, like kind of the rebirth of them. And you can kind of see that from this really good Vice headline, the 90s hacking trick making a comeback, right? We thought we'd kind of solve the macro problem, but here we are sort of dealing with them. Kind of the final sort of introduction slide. This is a little bit anecdotal. I don't have, this presentation is about this, but this is a screenshot of 2007, and I noticed that the old way to enable macros had this options button. So you push this, and you'd get another menu. Then I think there was a radio button. You had to choose something, and then an OK. So 2 to 3 clicks. Whereas in Office 2010 and later, they kind of simplified this down to enable content. So this didn't help. I guess that's my point of this slide. Okay. I've told you about this malicious macro problem. I can tell you how to solve it immediately. And that is, if you can block any document coming into your email gateway from outside that has a macro, just do that. The problem with this approach is that, like I was saying before, commerce is really conducted through a lot of the use of a lot of these documents. So unfortunately, for the product we sell, we are given unknown Office documents with macros, and we're expected to give a verdict. But if you can do this, please do it. We don't have that option. I know a lot of people don't. So so the rest of the talk now focuses on malicious macros and how we can better classify them for a threat intelligence perspective. So the data set that I worked on for this project was from the month of August. And what we're looking at here is a count of unique SHAs, so unique files that were Microsoft Word documents, so .doc or .docx. So Excel I kind of excluded from this data set. And these are the number of unique ones that customers send us to get a verdict on. And these are the number that get to the sandbox, which is kind of the end of a long chain of services that could give a verdict. And so once it gets to the sandbox phase, we open it and observe behavioral actions that the document takes when it's opened, and the macros are enabled. And so the data here kind of demonstrates a typical work week. So the peaks here are Monday to Friday, and then when less people are working, basically, Saturday and Sunday are much lower. And you can see we average about, during the work week, about 4,000 unique office documents with a macro. So this is both clean and malicious. So we've got 4,000 unique ones every day to try to classify. Okay, so the goal of this of my work was not to classify. We already had that information. We already knew which ones we gave a clean verdict to and which ones we gave a malicious verdict to. So of the ones that we gave a malicious verdict to, we wanted to supplement the data. Not only is it malicious, but can we give any kind of data about the threat actors involved, any changes of the payloads over time and tactics, as well as our customers are always interested in finding targeted attacks. So if it's something really unique to a specific set of customers, that would be interesting from a threat intelligence standpoint. And from a personal standpoint, I would just love to handle the malicious macro problem and never look at Visual Basic for applications again. Okay, so back at the beginning when I showed you a number of the sample documents, they all had an image in them. And over time, when you open up these things and start looking at them, you notice that the same image comes up and over and over again. So there was a kind of an idea of, well, what if we extracted every image that was in the document, hashed them, and looked for overlapping? So exact image matching. So this is the exact same slide I just showed. This is the volume of total Word documents with a macro. And this is, over that same time period, this is the malicious count from that set of unique documents. And you can see right away that there is no kind of day, work week pattern here. It's just sort of random. It's a little bit spiky here in the early part, flat for a while, and spiky at the end. Sort of the first question that might come to mind here is, well, what happened here? What's going on here? Because this graph is showing unique samples, there's actually, there are spikes here if you consider the identical file. So we do see the identical file sent to like multiple customers, but when their files are identical, we don't, it's sort of easy to deal with them. So this is totally unique counts. And so what we kind of wanted to do was account for some of these spikes and say, yeah, we know these are malicious, but what more data can we tell about them? So using the image hashing, extracting the images, and then grouping them based on that, we kind of come up with this grouping. So what I'm showing here is the top 10 groups in terms of count of unique documents that contained an identical image inside them. So kind of right away you see some of the spikes are accounted for. So this blue group 1, which is the largest group, had 800 unique documents had the same image. And then it's interestingly, it kind of spikes, drops off, spikes again, and then it's kind of gone for the rest of the month. What we see here too is group 2, which is the green. Again, kind of was falling as the month began, spiked, and then had a little bit at the end. Okay, so that's kind of interesting. So we've now grouped documents that have identical images in them, but what more can we say about them? Well, we have some sandboxing data or runtime data, what happens when you open them. So looking at just this group 1, just group 1, if we pull out the runtime data from the sandbox, all of these documents here were contacting and downloading the exact same next stage payload. So all of these all 800 of these 800 odd documents here were all contacting the same IP address and getting the same payload. So that kind of lets us start being a little bit more confident in the grouping of these. And again, it's the same for all of these. Now, if we look at group 2, just looking at the top 2 groupings of documents, the green, which all share an image, they're actually downloading the exact same payload that the blue group is downloading. So both of these, the group 1 and group 2, using within each one they use an identical image, but their first stage payload, the place that they're downloading their first stage of malware from, is from the exact same location. So if you saw the keynote earlier today, it seems like this was a kit, right? It seems like someone had some automation to generate these documents. They all included the same image, and they were after the same kind of payload. And there was a second kit used, or maybe a second automation solution used to create group 2. And what we're hoping to do over time is to determine, are group 1 and 2 the same people, or are they different? What's kind of interesting is that group 2 falls off to 0 on the 4th, and suddenly group 1 shoots up and falls down. Like, they don't kind of coincide with each other, so we're kind of hoping this research is going to help us track when we can do subsequent groupings on this. And you can see that there's a lot of smaller groups as well. Just to show you the two documents that came out. So this is group 1 here on the left. Kind of interestingly, their automation solution that built this document, this is the image inside it, but it's actually not visible when you open the document. So the forensics tools I used, which was just Foremost, if you're familiar with that tool, it extracts this image. This image is inside the document, but it's actually not visible when you open it. And on this one, the image is very much open. So over the month, there was 1,500 of these. There was around 1,000 of these, and they both were downloading the exact same payload. So from an analyst standpoint right away, you can say, okay, well, these 1,500, I kind of understand all of them, and then I can look at the payload, get some runtime data from when we open them, and describe this group that's sending them, and supplement our convictions with that kind of data. Okay, so an incredible number of the documents have images, and it was kind of useful to group them in the exact image hashing method. But there was a small number of documents that didn't have any image data to hash, right? So that the technique previously described wouldn't work at all. So for these documents, I wanted to try something else. So this is both .doc and .docx. So to do the subsequent work, I then separated them into the old format, which is .doc, and the new format, which is .docx. So this graph is both, and this subsequent graph is just the old style document. CDF is another name for it. It's basically .doc, the older Microsoft Office format. So again, you can see a spike. Now we're talking about a very low volume of unique files from what we were looking at in the previous graphs. But again, you see a kind of a spike and then a trailing off. So the idea here was I had no image data to hash, but I started to look at the format of a .doc file, and I wanted kind of something simple that was similar to the image hashing because that was somewhat successful. So what I just did is hash the streams. So a .doc file is made up of named streams. So I just extracted all the streams and hashed them. And so that gives you like a set of hashes of streams that are inside a document, and I do that for every document, and then look for intersections between documents. And there's a little bit of logic here. Some of these streams are not useful for this purpose because comp object streams are often the same between documents that really have nothing to do with each other, whereas some of these other streams, like anything to do with VBA is often the same, or Word document. So when the kits are building these documents, they're assembling the document programmatically, and a lot of these contents are not changing between. They might be re-obfuscating the macro that's inside, but some of these other supporting streams are remaining the same. So that's how we're kind of able to match them up. So the results of this were, again, we get a number of groups, but interestingly, some of the spikes, again, were accounted for. So the early spike we saw in the data, that actually flowed into group 2, the second largest group. And you can see that it came up here. There's a little bit at the end. And again, okay, was this a good grouping? Does this make sense? Well, we can use the runtime data from the sandbox to see, yes, these are all launching PowerShell in the exact same way. Looks like they came from the same kit. And if we can keep track of this over time, when this group comes back in September, we'll be able to maybe say something more intelligent about it than, yeah, it's just malicious. And the results from the docx, so this is just the docx samples over the month. Again, we have a spike to account for and some background noise. Docx's don't have stream data, it's a different file format, but they're zip files. And so inside the zip file, there's a number of files. And so in kind of using basically the same method, instead of taking streams, I just took the internal files, hashed them, and again, looked for intersecting sets between documents. And again, some of these are not useful. I threw them away. So anything that ends in .rels is generally not useful, so these get thrown away. But some of these XML files and VBA project files are excellent for grouping documents that come from the same kit or the same group. Again, so what was kind of encouraging about all this work is that the spikes were starting to get accounted for, whereas grouping the internal files accounted for the big spike we saw in the middle of the month. And again, using the sandbox data, the runtime data as a verification, these are all actually related. So this kind of work it's ongoing, and the idea is that we're going to keep track of this data over time, and as more malicious documents come in, if they fit into one of these groups, we'll be able to supplement our data. We've convicted them, but we'll be able to supplement, like, oh, this is usually ransomware, and now they're distributing something else. Or we have all these malicious documents that we can't group. What's special about them? What is making them different? Are they doing something different? Is it a new tactic? And when we see spikes, we're hoping this technique allows us to account for them. So we're going to segue over to Josh, and Josh is going to take us through the rest of the presentation.
So just so you know, if any of you are ThreatGrid customers or potential ThreatGrid customers, Cisco brought us here today. So a lot of those extracted artifacts you can actually pivot from our sandbox, and we have a giant Elasticsearch cluster that you can search for any other samples that have the same artifacts. So just a commercial plug there. But so so a lot of you are going to say, okay, you're hashing image files, whatever. That's lame because you have a cryptographic secure algorithm that's going to look for a single image file, and if you were to change one single pixel of that image file, then it's going to have a different hash, right? So for this talk and for our research to feed back into our product lines, I was looking at maybe some kind of fuzzy matching algorithm that we can use with images to cluster them together rather than using hashing mechanisms that will only look for exact matches. So I was reading a whole bunch of academic papers by Google on scaling for looking at duplicate images within their engine, but I thought we could use something a little bit simpler. The OpenCV project is fantastic if you're going to use if you're going to do any image research or video research. They have Python libraries, Python bindings, C++ bindings that provide a really good way of working with images. I found their ORB algorithm, which is oriented fast and rotated brief algorithm, is fantastic for clustering images. And then essentially what I did was take a known malicious, or a image that's known to be malicious or associated with malicious documents, and then I used that as a seed image and then compared it against all what we've defined as being clean documents for a certain amount of days. And then if a number of those features that we've extracted from the image match any of those supposed clean documents, then we know we've missed them, right? So this is known as feature extraction. I'm not going to try and fake my way through a lot of the computer vision theory because I don't have a major background in this, but OpenCV's libraries made this actually quite easy. And then essentially I established a certain percentage of matching features extracted from both documents, and if that certain percentage and ceiling was met, then I bucketed it for later review. So here's an example. So OpenCV will do this for you, where you have two images. The one on the left is known to be a part of a malicious document, and then the one on the right is from a supposed clean document. So this provides some fantastic feedback because obviously in this case we did not classify the one on the right as malicious, but what was occurring was within our sandbox it had an auto close macro. So the macro is only executed upon document close. Yes, this is a feature. Why it's a feature, I don't know. but they were using that to execute their malicious code only when the document was closed. Now, ThreatGrid recently released some functionality called playbooks, which automatically closes documents for you. So now we have an actual solution from the feedback from this research. This is a more interesting example where extracted features on the left image was actually a part of a smaller image embedded within a larger image. So in this instance, this was actually looking for, supposedly looking like a fax document, and then it had essentially a social engineering message embedded within it, a smaller image that had the same features as the image on the left. So that was a really cool product of this research. So great, we're talking about this from a high level point of view of trying to track these documents within our sandbox, trying to extract features to designate them as being malicious. But what about the actors themselves? So we actually just put out a blog on the Talos blog, the Talos Intelligence blog, which is fantastic if you haven't looked at it, the entire blog, and our post goes over this in detail. But there's a Fin7 threat actor that's essentially been active for a large number of years. They're financially motivated. They deploy and target a large amount of financial institutions, hospitality, and medical industries. So it's essentially applicable to everybody in this room because we all use banks, we all go to the hospital sometimes, we all go out and eat and stay at hotels. So they're targeting all these campaigns with financial motivation of stealing money. And they're typically using spear phishing techniques with documents, so I'll be going into one of the documents today, and this is constantly changing and evolving. So from the month of July and August, we were seeing some odd 30 documents from this threat actor alone that they had changed their techniques and tactics quite frequently, and this was to avoid antivirus detection. Okay, so they are constantly monitoring blogs, they're constantly monitoring antivirus services for them being detected, and then they'll change their techniques and then go on another campaign again. And they're also leveraging public tools. So I commonly get in an argument with one of my pen test friends over the release of penetration testing tools. So this is an example of they're literally copy-pasting code from the PowerSploit project and using it in active campaigns against financial institutions. So anyways, take from that what you will. So document analysis, let's actually dig into a document and look at it. So the nice people at Cisco made me this beautiful graphic. So I'm just going to move through each component of this document using this graphic. So this is an RTF document, which you can see up here. This is what the document looks like. So I'm not sure if you know this, but within Office documents, if you drag and drop a file, it becomes an embedded OLE object within that document. So in this case, the document contains a OLE object that's an LNK file. Okay? So for those of you who are not very well versed with Windows, LNK files are simply link files. So if you were to right-click on a file and make a shortcut, that's an LNK that will link to an executable that you can execute. But what a lot of people don't know is you can actually embed commands within LNK files, and those will be executed. So if somebody sends you an LNK and you click on it, they can actually get full remote code execution on your box. And a lot of people don't know that. But these guys embedded an LNK file within the document itself. Okay? So what they did now was they execute WScript. Okay? So this is the Windows scripting host on the Windows operating system that they're executing from an LNK file within a Word document. Okay? I'll try and space this out as much as I can, but you can ask questions afterwards if it gets complicated, because it's going to get complicated. But essentially, they were executing WScript, and this is the command that they were executing. So they were doing command.exe, and then they were using WScript to execute JavaScript. Okay? And when I found this, I was amazed. From WScript, you can reference an open Office document, okay? They were extracting JavaScript from within an active document object within the open document. So this is an external application that can actually pull out data that's in an open document, okay? They write this to disk in a file called md5.txt under your home path, and then they execute that, okay? So then what happens is a large series of base64 decodings from JavaScript. So now we're strictly executing JavaScript from the Windows scripting host. So for those of you who don't know, the Windows scripting host allows you to execute JavaScript, and you have access to ActiveX controls and things like that. So this is very different than when you execute it in a browser where it's completely sandboxed from the operating system environment. When you use JavaScript on Windows with WScript, you actually have access to the full operating system for the most part. So here we have, this breaks up into a whole array of JavaScript files that have a whole bunch of different base64 decoding steps. So I'm sure many of you in the room know what base64 encoding is, but basically it's an encoding format for any type of data. They've done anywhere upwards of 8 encoding steps of base64. I'm assuming this is to avoid any antivirus emulation that will be attempting to emulate this JavaScript, because they'll only do a certain amount of iterations, otherwise you're going to kill the machine that you're running your AV on. So, and we basically just built a custom Python script that would extract and automatically decode all these base64 decoding blobs, and then in the end we ended up with almost 40 some odd JavaScript files for a single document. Okay, so this is basically what the base64 decoding looked like. What was interesting was the char set that they're setting for this base64 decoding function is Cyrillic, which could actually indicate Russian origin. Take from that what you will. And then here we have the evaluation of the base64 decode. Okay, so this basically made up a series of JavaScript files, and a series of JavaScript files that actually made up a JavaScript botnet from a single document, okay? So now, as I said, we had 40 some odd JavaScript files from a single document. That's a lot to process and go through manually, and of course I'm lazy and a programmer, so I was like, okay, I'm going to write code to do this for me. So essentially, if we wanted to cluster this JavaScript, we have to extract certain features, okay? So for extracting attributes from the document, we have, like I said, 40 some odd files, and I wanted something simple, so I used a scatter plot. Okay, so within the scatter plot, I used R. For those of you who are working with any data, I highly suggest that you use R for any type of analysis like this. There's a lot of supporting Python libraries as well, like SciPy and stuff like that, but for this, I used the ggplot and ggiraffe R libraries, which are fantastic, to plot this within a scatter plot. And for one of the axes, we used the base64 decodings. So the amount of base64 decodings required to get to that JavaScript file, and then entropy. Okay. So for those of you who don't know what entropy is, essentially it's the calculation of disorder and uncertainty with any given amount of data. So essentially, it's looking for randomness within any given amount of data. But we can use that for clustering JavaScript files, because you can have essentially any related code would technically look the same in terms of randomness, but it could be different in terms of actual textual content. So I'll show you what that kind of looks like. And then, so what we got out of this was essentially this. I know it's pretty small, but essentially, we got clusters, which I was amazed that this actually worked. This is the first thing I tried, and I was like, awesome, okay. So up here we have, so these are all different JavaScript files that have different bot functionality. So in the top left, we have scheduled tasks that are executing each part of the botnet that's made up of JavaScript on your system. Then we have like WScript, JavaScript execution. Then we have the botnet command and control commands that were clustered together using this technique. And then we have like base64 decoding steps and a number of other scheduled task areas. So the conclusions that we can extract from that clustering exercise are pretty significant. Like obviously, with the higher depth of base64 decoding, we have more interesting functionality, okay? So that's to be expected because they're going to keep their most interesting functionality for the most amount of decodes. And we were able to cluster these bot functionalities into multiple different sets of files. And this showed us that essentially they were changing their algorithm each time, where we would have a large number of different files, but they would have the same functionality in different encoding steps. And then like another variance of what I just mentioned is essentially that we have the task scheduling functionality that varied in decoding depth. So essentially that shows us they're changing the amount of decodes that they're doing in every single document iteration. So this is an example. It's super hard to read, I'm sorry. But essentially, this is the base64 decoding JavaScript block, and you can see they did some function reordering. So these are the same functions, but they have different order. But we were able to cluster these using entropy and the base64 decoding depth, and that essentially showed us that they're doing some function reordering within the JavaScript in each document iteration. And then here you can't see it, but they're renaming variables. That's another change that they're doing through every document iteration. So here you have BE, and then you have renamed functions over here. Some of you might notice this large, like this is just color-coded Vim, but you can see this large comment block, or what looks to be a comment block. So I was super confused when I started looking at this, because I was like, so they've commented out this functionality. Well, it turns out that with a large comment block like this in JavaScript, you can actually use the toString function, take a slice, and then you can eval that. So it's actually, this is a JavaScript evasion mechanism for emulation engines, is what I suspect they were using it for. But like, this is insane, right? Like, you think a comment block wouldn't be able to be turned back into a string and then you'd be able to evaluate it, but apparently it's true in JavaScript. And actually somebody in this room helped me with that, so thank you. And here's just an example of this in the Chrome console. And I say, I can't believe this actually works, and it does. So that's another interesting technique that they've employed. So as I mentioned, with that PowerShell code, what they're actually doing is in one of those final decoding JavaScript documents, they've essentially gotten to the point where they execute some PowerShell, okay? And that PowerShell is actually decoding an entire portable executable, and this is all within the document, okay? They're decoding an entire portable executable, then they're using PowerShell from the PowerSploit project to reflectively DLL inject that into memory, and I will go over the actual functionality of that malware. So here we have code that was copied and pasted from the PowerSploit project. It's a function called invoke reflective PE injection if you want to use that, if you want to look at the function itself. But essentially what it's doing is, if you don't know how reflective portable executable injection works, or DLL injection works, is that essentially you're loading the DLL into memory yourself. So you have a custom loader, you're not depending on the operating system to do it for you. And what this is commonly used for is an evasion technique where if you're calling an operating system API to load a DLL for you, that's commonly hooked by a large amount of antivirus engines. But if you're loading the DLL yourself without the assistance of the operating system, then you can essentially avoid that. So, and then, okay, so we have this DLL that's being injected into memory. What is it doing? So I reversed this, and they had some similar functionality to a malware variant that we looked at last summer. You can look up the H1N1 blog that I wrote on the Cisco blog. But essentially, and they had some import hashing, which is very common for malware. But their end goal was to steal Firefox, Chrome. They were targeting Chromium forks, IntelliForm data from Internet Explorer, Opera, and Outlook login data. Okay. So essentially, the end goal of this DLL was to extract your passwords and then send them back to a command and control server. And here's an example of, I go into all this functionality in depth from the H1N1 blog that we published last summer because they're using the same techniques. But it's interesting with the IntelliForm data, they're actually encrypting. So in Internet Explorer, when you're prompted to save your password, it essentially says, when you say yes, it's actually storing it on the system, but it's storing it in an encrypted form. And the way that the Windows OS does this, it might have changed in Edge or the newer Internet Explorer variants or versions, is that they will SHA-1 the URL that you used to log in with, okay? And then they will use that to encrypt your password. So every single time you hit a website, it'll automatically SHA-1 that URL and say, oh, I have a password for this, and then it'll insert it. But what they actually did, which was pretty clever, is they used find first URL cache entry to find every single cached URL entry on your system, and then they'll SHA-1 those, and then try to decrypt your password with each of those SHA-1s. Okay, so they basically decrypt the functionality that, like, I know Microsoft doesn't really consider this a security boundary probably, but I thought that was quite entertaining. And with all these other browser variants, you can use a Windows API. I think you have to be administrator, but if you're administrator, you can use, and logged in as the user, you can just use, I think it's Crypt Unprotect API on Windows to decrypt your passwords. And they do this prior to sending it back to their command and control server. So what does that look like? So once they've extracted your passwords, they essentially write it to appdata username .ini, and then for whatever reason they're changing it to the timestamp of the write for that ini file is changed to that of ntdll. I'm assuming this is an anti-forensics mechanism where essentially if you diff the files on the system that were changed for the past day, you wouldn't see this password file because they're simply setting it to the timestamp of ntdll, which would be changed maybe since your last Windows update or something like that. And then this is encrypted, and then periodically using a scheduled task from that extracted JavaScript is periodically posted to a remote command and control server. And then this is essentially what that encryption algorithm looks like, and it's a basic substitution cipher. So if you were to see this command and control traffic, you could decrypt it in line and see that your users were compromised. And then here you can actually see the alf in and alf out variables, which are initializing those alphabets for the substitution cipher. And then you have some hard-coded IPs here that are the command and control servers. And then what was also interesting, which a number of other people have talked about with Fin7, is they're using the Google Script hosting service as a command and control server as well for backup. So say this IP is down, then they can still rely on Google to get their stolen passwords, which are encrypted using that substitution cipher. So yeah, and then essentially all of this is just implemented in JavaScript, their entire botnet functionality. So I know I moved through that really quickly, and I'm surprised we're not over time, so I'm sorry that I went through that really quickly. But if you guys have any questions, I think we're going to post up the slides somewhere. Hopefully maybe I can talk to Steve about that. But if you have any questions, yep. Do we have a mic? Want to add anything? Do you want to add anything?
So great presentation, guys. Thank you. When was JavaScript given system-level control in Windows?
So I'm not exactly sure when this occurred, but effectively, Windows gives you access to the Windows scripting host to perform scripted tasks for you, like any scripted task. And what gives you like code execution control or system-level access is actually the ActiveX objects that you can access from the JavaScript itself. So in this scenario, they were able to, say, execute PowerShell from an ActiveX object. And yeah, so I'm not exactly sure when that happened, but I do view it as being, like, in reality, this could be done with any other scripting language. So if you were to compromise OS 10, and Metasploit will do this too, is it will use VBA with an embedded macro, and if it checks that the operating system is OS 10, so like Mac OS, then it will use Python. So in reality, like they could have implemented this botnet functionality with anything, but they just chose to use JavaScript because why not? There are, this is like an entirely other talk, or sorry, a whole talk in and of itself, but Microsoft is working on a large amount of engines to automatically deobfuscate this kind of stuff. So that's something to keep in mind. Chris talked about a few of them, which the ATA and ATP product lines are making use of, but we've actually been looking into leveraging some operating system APIs provided by Windows on Windows 10 for automated deobfuscation. But as of right now, we do have pretty decent coverage of even obfuscation techniques. Like a lot of the work that Ross and I do is looking at these attack methodologies and see how they change over time, and then we provide that feedback back into the product lines that we work on. So yeah, here's some resources.
We got another question.
Sorry, where was it? Oh.
Yeah, excellent presentation, guys. Thanks very much. Quick question. You have a, don't want any feedback here. You have a document file in it, and it's got a macro in it.
Yes.
Is there any way you can simply tell just by looking at properties or something whether there is actually a macro in the document?
Yeah.
Because that's almost like a fairly easy step one check.
Yeah, absolutely. If you save them manually, newer versions of Office will insist that you save them as a docm, so it gives like the user a clue. Generally, the icon is different too. Depends on the versioning, but there'll be an exclamation mark or something other indicating on the document icon. The trouble is when they come in through email, that's not always noticed or not always obvious to the user. So, in my opinion, your email solution should be able to detect that. Like that would be like a must-have feature of like incoming. So as an end user, so thankfully to Mike. Yeah, so the question was about an end user that maybe doesn't have access to like an enterprise security solution. What do you do? So them being disabled by default is a very excellent thing that Microsoft did. And the problem is that I know a lot of people are in the habit of just enabling that all the time, especially if you're used to getting them from colleagues or something, and that's how you conduct business. It's like muscle memory just to enable the content. So that's one of kind of in my opinion, deficiencies with that approach is that you've trained users just to click without thinking. So at home, if it's just a macro and doesn't contain an exploit, if you don't enable it, you should be okay. You should, if you have default settings, you should be notified, and don't be in the habit of enabling every time.
You can just disable macros by default, and then if somebody sends you a document, like as an end user at home, like if they're like, oh, you need to enable macros, ask them why. Like really for a Word document, like in what's like, they're like, oh, I want my like dynamic banner to like fly across the page when you open the document or something, right? Like there's not really any valid use case for a Word document to be open with macros in a normal end user scenario. With like Excel, it's a little bit different because you do have a whole bunch of logic that you can implement in Excel using VBA. But yeah, for an end user, I would honestly just suggest not like just disabling them by default. But if you do have, you will get that warning if you do have the default setting enabled within Office. So you'll always get that warning unless you say, like I think there's an option for always execute macros, which is obviously the worst.
Can you still find if there is a macro in the document by looking at the properties?
I'm not sure about CDF. I know for docx or that format, the newer format, you have to have docm, or else it will not. You have to have docm as the file extension, or else it will not like attempt to execute those macros. But yeah, I'll have to actually have to check for CDF. You can see in our stuff, but obviously you don't have access to that as an end user.
Right.
Another question. So, how would you guys rate the complexity of this attack with regards to exploiting Office macros? And going back to your statement about Microsoft not considering the hashing of the URLs a security issue, what is your overall thinking behind that, and is anybody else using that same technique to store passwords locally?
So can you repeat that first question? It's hard to hear with the vendors.
Yeah, so how would you rate the complexity of this attack? Like initially looking at, with regards to exploiting Office macros, initially looking at this, I'm like, wow, this has got to be seriously targeted at C-level executives, but then it's more of a user behavior issue because people are storing their passwords foolishly in their browsers, which would obviously be circumvented by use of a password manager, for example.
Yeah. That's so yeah, to answer the first question, the use of macros is trivial as an attack vector. Unfortunately, the end user doesn't understand these scenarios, and I for one would like Microsoft to provide macro functionality without having access to the operating system, like sandbox the macro. Like they don't have to have access to execute code on the box from a macro. And even if you have Office installed on your Mac, it literally opens up that exact same attack vector on an entirely different operating system. So you're literally porting a giant security problem to an entirely new operating system on your software that's used by millions, if not billions of people, right? Do you have anything to add?
No.
And then in terms, for password management, I use a local password manager. I think OS 10 has a better approach where they have a keychain, and then that is encrypted by your password. From the IE perspective, if they have access, in reality, if they have access to your local machine, they can probably just get your password in a million other ways, like keylogging or
clipboard logging.
Yeah, like a pop-up box that's prompting them that looks similar to another application, things like that for a normal end user. So I think they've kind of gone a step further than storing it in plain text, but I don't think it's that much further. But yeah, my suggestion would be for a normal user is to use a password manager, but I'm still not a huge fan of password managers either, so there's not really a great solution for the endpoint itself. If you can remember them in your brain, it's probably the best suggestion. But I know that's not really a useful suggestion. So, any other questions?
Yeah. Hey. In the entropy classification that you did there, you had the scheduled tasks on the one side and on the other side. Does that entropy clustering detect differences between authors of files in that?
No, so we know these are based on the attributes and the way we're tracking them. We know these are Fin7, so we know they're the same actor. In theory, we could definitely use entropy. I was only using a fixed byte size for the entropy calculation, so that could be the task management code was up here, and then the task management code was up here, and that's the large reason behind the entropy change. So this is not an exact science. It was kind of here's what I tried. These were my results, and I think you'd find them interesting. Could we scale this for large clustering of large different samples? I'd like to reach that with the OpenCV image clustering because I think that shows a lot of potential. But for this scenario, since we were using base64 decoding depth as one of the axes, I don't believe that it could be really applied elsewhere unless we see base64 decoding depth being used again. So this was almost just for clustering the Fin7 documents themselves. And then once, what I kind of didn't really mention that well is that the reason I did the clustering was to look at those minute changes, which then I saw later on when I was comparing the files within the clusters. But yeah, definitely it could totally be used to look at different actors. If you were this, the clustering field is huge. So you can have k-means look at X number of different dimensions of data, but in this instance, I just used a two-dimensional scatter plot. I didn't use k-means or supervised or unsupervised machine learning or things like that. But there's definitely a whole bunch of different computer science fields that can be applied to this problem.
Hello. Hey. So I have two questions. You had an image matching thing on Word. Did you find any false positives with that, like without image matching at all?
Yes. Yeah. Like, basically, I was trying to adjust the required matching features to the point that we weren't getting false positives, but it was difficult because, for example, when I turned it down to the point, the number of required features matching to the point of getting that embedded image within another embedded image, then I was getting more false positives than if I cranked it up, and then I was almost getting exact image matching for extracted features, even though they are different hashes. So yeah, it's still, again, this is like essentially something we've tried. I'm going to try and make it scale, and then see how it performs in giving us, like, one, we're using these images for classification of malicious documents, and then two, we're using it for feedback into what we're not classifying properly within the sandbox.
So I meant the SHA image on the Word documents. Do you find any clean documents that also included that image? And also, I want to hear a little bit about your takes on what techniques do you think Microsoft can do besides obviously disabling macros at all to lower down the amount of malicious things that documents can do with macros.
As far as the image matching was good because it was exact. It was good at finding documents we misclassified. So there was documents that were marked as unknown that were actually malicious, and that was because they had the same image inside. In most of those cases, it was finding things that were corrupted, so that they'd been altered in some way, so they actually didn't open. We didn't have a lot of behavioral data, so it was difficult to classify them. They were also impossible to be opened by an end user. But we're not seeing, for the exacting, I couldn't find any examples of clean documents using those images because they're very focused to social engineering, and it just didn't make sense. As far as the macro problem in Word, having users click through it is no solution in my opinion. So Office 2016 I know has a bunch of features that allow you to, if you run an Active Directory domain, you can secure that, you can ensure all your individual users are secure. The only thing I could, Josh mentioned it already, is some kind of sandbox approach. I've looked at a lot of clean macros. You're going to break a lot of them. So I think that's the conundrum that Microsoft is in. They know they could add a sandbox, but there's all these macros that commerce is basically, people's invoicing systems are based on these, and they're running, they're often, it's at least push button or the user has to interact with the document more, but still they're executing PowerShell from totally clean documents written by, I'm talking 5,000 line macros and stuff like that. So.
There's also actually macro signing functionality that Microsoft offers. So if you're in an enterprise environment and you can enable macro signing, that would be good. But again, if Lucy in HR gets popped and then you get her signing key, then you can just sign macros and then send it to the rest of the company. So I'd like a permanent kind of approach of the sandboxing methodology where just restricting access to the operating system itself seems logical to me. It's like having, I don't know, Microsoft does this shit all the time, right? Like in IE, you used to be able to enable ActiveX controls from a website, and then you could just get code execution. So anyways, I know it's not an easy solution for them either because they're going to break millions of environments. So
I think it's lunch. Thanks a lot.
Yes, it's lunchtime. Thank you so much, guys. That was awesome. We'll be back in this room at 1 o'clock.